Hi everybody, in this video we are going to be talking about torque. Alright, let's get started. So before we start this discussion about torque, it is imperative that you have already watched the video on rotational inertia, because the ideas of rotational inertia will come back again when we are talking about torque. Okay, so to start off, there's actually two equations that we can use for torque, and we'll go over both. Now, when we are writing the equation for torque, the variable that we use for torque, it is not a capital T, okay? Because if you remember, that represents period. It's not a lowercase t, because that represents time, but in fact, it is a tau. Wow! So it's kind of like a T that got a little bit fancy, put on a little hat, and kind of has like a kick in its step, right? And then we pronounce it as T-A-U, tau. And tau is a Greek letter. Okay, so torque. What is torque? If you remember from the kinematics video, there's a lot of analogies that go back and forth with the linear stuff, the translational stuff, and the rotational stuff. So let's take a look at the linear version of this. So to start off, torque is analogous to force. Okay, and if we know that the equation for force is mass times acceleration, the net force is equal to the system's mass times the acceleration, we can say the same is true for torque. Okay, so torque is a lot like force, and instead of saying m for mass, we can write it as I for rotational inertia. Okay, see where that popped up? And instead of saying a for acceleration, we can say alpha for rotational acceleration. Okay, so this is version number one. Version number two is torque is equal to the force exerted at a radius away of a moment r. All right, so we have two versions of this equation, and we're going to go over exactly when to use either one of those equations. All right, so to start us off, the units for torque. We could take a look at equation 2 because that will really help us. The units for force is, of course, the Newton, and the units for radii, or aka the distance away, is meters. And so we get the units for torque as a Newton meter. Okay, a Newton meter. All right, let's go over. I'd like to start off with the first one. Okay, tau is equal to I times omega, or torque. So this is version 1. Torque is equal to I times alpha. All right, so let's break this down. Much like F equals ma, we can use this equation in the form of a sentence. All right, so let's have a object. There's an object on the ground. Let's say m, and we're going to exert a force on it, going to the right. And when this happens, this object will accelerate. Okay, it'll accelerate to the right. So if I were to write this in a sentence, right? If I were to write this equation in a sentence, I would write it something like this. If a system, now remember, we can say that system can be described as like the mass, right? AKA the mass experiences an outside net force. Okay, so that's where the F comes in. The system will accelerate. Okay, so within that sentence, we have F, we have M, and we have A. This is a quick little reminder, and this is one of those red star kind of moments, very important, that acceleration means that a object is either speeding up, slowing down, or changing direction. And that's important for our discussion from here on out. Okay, so all right, so that's when we have a object that's experiencing a force and is moving in like a linear kind of direction. Now, what about a rotating object? All right, so if we have a object that is rotating or spinning around, so let's say like a top, right, or like a disc. Okay, so we have a disc. So this is kind of like an aerial view, like you're looking top down into it, and it's rotating, kind of like a record player. Okay, so it's rotating around and around and around. Now, according to Newton's laws, this object will rotate, aka spin, for infinity. Okay, unless there is a outside force. There is an outside force, and we call that outside force the torque, right? All right, so if this object is spinning, there's two things that we can do to it. If we want to make it spin faster, we can exert a force on it. If we want to make it spin slower, we can exert a force on it, right? So if you were to imagine this, right, if we were to push it in the direction that it is spinning, it'll spin faster. But if we were to like push against it, it'll spin slower. And you can imagine this kind of like tires, right? If you have a spinning wheel, okay, and the wheel is spinning and you push it in one direction, the direction that it's spinning, it'll spin faster. If you go against it, kind of like brakes, it'll slow down. So let's turn this equation into a sentence, just like what we did over there. So I is the system, right? If a system, aka the rotating object, or the rotating system, experiences a net torque, the system / object will accelerate. Okay. All right. So I'm going to highlight the variables. Okay. And just as a little caveat, remember acceleration, it can either spin faster or spin slower. Okay. All right. So that's the idea behind this torque idea, right? If you have an object and it could, it doesn't even have to be moving, it's just like kind of there and it starts to spin. Or if you have an object that's already spinning and it's slowing down or speeding up, and that's because there is a net torque. All right, so what I'm going to do next is I'm going to just have a couple of pictures just to really demonstrate what this really means. Okay, because we have like two versions of the equation, it's good to know when to use which one. So let's say we have a spinning top. Right, I'm going to do my best to sketch here. So we have a floor. Now, if you were growing up, and you were a little bit older, you might have had a top to play with, or you gotta have a children's toy called the Beyblades. Gotta bring them back, or we have like fidget spinners. Yeah, if you remember fidget spinners. Okay, so we have a object, this top, and it's spinning around and around and around. Okay, and eventually, because this object is making contact with the ground right there, I'll put a little red mark right there, the object this top will slow down. Okay, all right, so this top will slow down. And if you were to ask me, or if I were to ask you, why does it slow down? A very common answer, a very popular answer is because a force of friction. And I would say very good. Right? And so we can describe it using this equation. Torque is equal to I times omega. In this instant, this is the top, right? This is the spinning object. The force of friction will exert a torque, right? So this is the torque due to friction. And this alpha is the top slowing down. Okay? So if you might be catching on with this unit, I'm using a lot of concept and a lot of ideas to really describe things so that we can bring these equations to life. All right, so that's one of the scenarios that you have right there. Okay, let's try like another version of this. All right, so let's say we have a record player, right? So we have a record player, that's the middle of the record. Okay, and then this is like the record itself. Okay, and so if you go over to like your grandparents' house, or I don't know, record players are kind of making like a comeback, right? There's like a box, and like the record player kind of like the record kind of sits on top of it, and it like rotates around and around. And there's like a needle. I've never seen a record player before, so I'm just kind of making this out, right? There's a needle that kind of pushes down on the record and makes noise. So if this record player is spinning around and around, and you're part of the up-and-coming DJ crew, right? So you're part of a DJ crew. You're a DJ. Your name is DJ Physics. Okay, Physics, and you're joined by DJ Torque. All right, you're a duo. Okay, DJ Physics with DJ Torque, right? And then you have two turntables. So every time, right, so this is my turntable motion. Every time you put your hand on the spinning disc and you push it, right, you're going to change the rotation. Let's do the rotation here. You're going to change the rotation of the record. And that's because you are exerting a outside force. And so the torque is equal to I omega. And in this case, this is the record. Okay, and this is your hand, or the DJ's hand. You can be DJ Torque, I'll be DJ Physics, right? And this is the record either speeding up or slowing down. So that just means like spinning faster or spinning slower. Okay, so that is how we can bring this equation, torque is equal to I omega, to life. Now, what about the other version? Okay, equation number 2, torque is equal to force times the radius. So let's take a look at that. Now, this one, I'll show you different instances here. So we have torque is equal to the force times the radius. Okay, so when we're taking a look at this, you'll notice that there is no rotational acceleration. So we're not looking to find the rotational acceleration here. We're just trying to see like what's happening to the system, aka how will it be affected. And so what I mean by this is, let's say you have a door. Okay, let's say you have a door. Oh my gosh, okay, I'm going to do my best to draw a door. This is a 3D door. 3D door. Oh. Okay, I'm getting a little, oh my goodness, I'm getting a little burst of inspiration here until this drawing program fixed my door for me. All right, so this is my door. Okay, oh my goodness. All right, this is my door handle. Let's see, this is my door frame. Oh, okay, and this back out here, this is like the outside world. Okay, this is like the outside to your house. And this is like the little part of the door that locks the door and all that. Okay, so this is the door. Now, the way that we can use this equation, force times radius, is when we want to see how the object will start to rotate, or how this object will be affected. So what I mean by this is, if you have a door and you want to open the door, right? So you will, put your hand on the handle, right? And then you'll either push or pull the handle. And so we can see this here. So your hand, I can't draw a hand, so I'm gonna draw a little. That's me. Okay, so that's my hand. I'm a stick figure. Hello, right? So this is DJ Physics, right? I'm going into DJ Torque's house. All right, so I put my hand on the handle, and I'm going to, it looks like in this case, I'm going to be opening up the door, right? And so the radii is wherever the hinges or the rotating axis. So right there to right there. So this will be the radius. Okay, and so that's what we call this idea. This is this moment arm. So when I exert a force, right, I am doing the pushing and pulling, and this force causes a rotation due to a force being exerted away, and that away is just a r, from a rotating axis. We can say that a torque, wow, was exerted on the object. Okay, so we would use this equation mainly if you're given the force and you're given the rotating radii. Okay, so when you're given this, you can find the torque. Compared to the other equation, I alpha, you can use this equation when you're given the accelerating or the rotational acceleration, and you're given the rotational inertia of the object. Okay, so see, like it's the same equation, but you can use it for this different cases. Now, this is really cool because this actually tells us why the handle to the door is always the furthest away from its pivot point. So what that means is you'll never see a handle like right here if it's rotating about this axis. And that's because the further away you are from the rotating axis, the more torque you can exert. And so this is where we come across the relationships. So if we see torque is F times R, right? The further away you are from your rotating axis, the more torque you can exert. So what this means is that you don't have to push / pull hard to get the object to rotate. Okay, and this is very important because this actually explains it like a ton of different things. One of the things is like why the handle to the door is always furthest away from the pivot point, right? So that's one of them. Another one is like let's see, a wrench, right? So if we have a nut, okay, and then you have like a wrench, woo, right? So this is my wrench. There we go. Okay, there's no point in pushing down right there on the wrench because this is the axis of rotation. Look at this. Look at this radius. That's a very small radius. Like if you're pushing down on that part of the wrench, you're not going to cause this this nut to spin, right? It's not going to spin. This nut's not going to spin. But if you were to push down all the way at the end, okay, look at this. Look at that radius. The radius is so big. And so what that means is you don't have to exert as much force because this nut will now spin because there's such a great torque. Remember, torque is the ability to cause a object to spin/rotate. All right. Now you'll get the concept. You'll get the hang of this once we do more practice problems. But this is the main idea here, right? If that's the equation, you should be able to see and understand why certain things happen once you adjust the different variables. And this idea, this torque F times radius, it's all over the place. We see that in so many different instances. One of them is just a door, one of them is a wrench. All right, now let's see. What else can we do? Let's do a quick little practice problem because I do want to show you that torque, multiple forces can happen at once. All right, so let's say we have a lever, right? And this right there, that's a fixed point. Fixed point, meaning that this object will either spin this way or that way, but this point right there, that's where the axis of rotation is. Axis of rotation. Okay, so let's do a quick little practice problem. So let's say we have F1, okay, and let's say F2, okay, and then we have like F3, and let's say we have, I don't know, I'll do one right here. Let's say this is F4, okay? And let's come up with these values. Let's say F3 is, I don't know, 2 newtons. F4 is, let's say 5 newtons. Let's say F1 is 1 newton, and F2 is 2 newtons. Okay, so we have, let's say like this is like a top-down view of a door, and this is like inside. That's like inside the house, and this is like outside the house, and for whatever reason, like, oh, zombie apocalypse, right? So you're inside the house and you don't want the F4 and F2. These are zombies, right? F4 zombie, F2 zombie. You don't want them in the house. F3 and F1, those are survivors. Okay, so you don't want them in the house, but these zombies, man, this is a super strong zombie. They're like, they want to get in, so they're pushing against the door. All right. So this is the axis of rotation. That's the door hinge. And let's say here, this is a radius of. I'm going to do a different color here. We'll say this is a radius of, I don't know, R. Why is that so thick? R is equal to. We use simple numbers, 1. Okay, like 1 meter or whatever. We'll say this is R2 and this is R3. Okay, so in given a problem like this, what you have to do is you have to find the net torque. Okay, more letters. Net torque. What is it? All right, so net torque, in this case, it's all the torques added up. So it'll be torque 1 plus torque 2 plus torque 3 plus torque 4. Okay. Now with this, you can designate like which direction you want to be positive and which direction you want to be negative. So for our sake here, we'll say anything that is counterclockwise to be positive, and for the sake of this problem, we'll say anything that is clockwise to be negative. Okay, counterclockwise positive, clockwise negative. Now, depending on the problem, that could also change, but for this sake of the problem, I'm going to designate counterclockwise as positive and clockwise as negative. So all you got to do here is find the torque. So we know that torque is force times radius, and we see the force of 1 being 1 with the radius of 3. So my torque would be 3 Newton meters. Okay, and because that's going to be pushing this object towards the negative direction. How do we know that? Because if it was just F1, this door will be swinging counterclockwise. I'm going to make that negative 3 Newton meters. Now let's try the same for torque 2. Torque 2 is a radius of 3 away and is being pushed by 2 newtons. So that's a total of 6. That's 6 newtons. Wow. Did I do my math right? Yes. Okay. 6 Newton meters. And because if it's just F2, it'll be pushing towards the counterclockwise direction, we'll say that is positive. All right. F3, torque 3, we have 2 times 1. So that is 2 Newton meters. And if it was just torque 2, it will be pushing this object in the the clockwise direction. So that'll be negative. And then our last one is torque 4. 5 times 2 is 10 Newton meters. And because that'll be pushing it towards the positive direction, we'll say that's positive. So we have negative 3 plus 6, which is 3, minus 2, 1, plus 10. So the torque, the net torque, is 11 Newton meters. That's what is happening to this door. So this door, which is, remember, I, experiences, I-door, experiences a net torque of 11 Newton meters. Now, here's the important part, because it's positive, the door will swing counterclockwise. Okay. All right. Now, this is what's cool. If you know the net torque, right, and you know the door's rotational inertia, you can determine the door's acceleration. So you can combine the equations. So we have torque is equal to torque. So I alpha is equal to F times R. Ooh, that's our final equation right there. So in the case for our survival story, bad news, friends. The zombies won, the survivors lost. All right. Well, that's that. That's the introduction to torque. The easiest way to go about torque is to just get some practice in with different scenarios. But until next time, I'll see you later. Bye-bye.